In this lesson, we're going to be learning about ellipses and how to graph them. Ellipses can be thought of as elongated circles or circles that have been stretched in one particular direction. Now, in general, an ellipse is considered the set of all points in an x and y coordinate plane, where the sum of the distances from two fixed points is a constant. Now, I know that seems a little peculiar, but what we mean by that is, let's just assume that we put two pins on our x-axis, and we tie a string to those pins. When we pull the string tight, the length of this string is never going to change. So when I look at putting a pencil at some particular point on the graph, then the sum of D1 and D2 is going to be the same no matter where you end up drawing on the graph. So if you keep this string tight the whole time, then this will be a different D1 and a different D2 than it was at the beginning. But since the string never changes size, the sum of those distances is always a constant. We refer to these two pins as the foci. This is one focus of the ellipse, and this is the second focus of the ellipse. So if I continue drawing the pencil all the way around, that's going to finally complete our ellipse. The center of the ellipse is always going to be midway between those foci. So let's take a look at a video which shows this in more detail. So if we were to put two toothpicks into a board and put a string around those toothpicks, we can now put a marker inside of that string and pull it tight. And now notice that the distance or the length of string is always going to be the same. So as he starts to move this marker around, you can start to see that the small distance and the large distance, meaning this distance to the pen and this distance back to the other focus, will change. So for instance, if we get to here, now notice the D1 is much longer and D2 is much shorter, but the string is always the same length. So when I continue to draw this and move this pen all the way around, I finally create the entire ellipse. And when we take a look at the standard form of an ellipse, we're going to see some variables a and b. And we're just always going to assume that a is the larger number. So we can see that the standard form for an ellipse looks somewhat like the standard form for a circle, where I see an x squared term plus a y squared term. The only difference is that now each of these quantities are being divided by some number. If the larger value of a is underneath the x term, then we know that it's going to spread more in the horizontal direction, so we'll have what we call a horizontal ellipse. But if the larger number, a, is attached to the y term, now that means that the larger number is going to cause the graph to stretch more in the vertical direction, which is why we refer to it as a vertical ellipse. Now we're going to start off by trying to find the x and y intercepts of these functions. So let's start with the horizontal ellipse. Notice that in order to find x-intercepts, we're simply setting the y-coordinate equal to 0. Now in this case, the y-coordinate is over the b term, while over here it's over the a term. So notice that entire term is going to cancel over here, leaving me with x squared over a squared equals 1, while over here we're left with x squared over b squared equals 1. Notice that the process is the same in both, so when we cross multiply, we get that x squared is equal to a squared, and therefore taking the square root gives me x equals plus or minus a, while over here we get x equals plus or minus b. Now this is a really helpful tool here, because what that shows us is that if we're trying to find the x-intercepts, then all I need to do is look underneath the x variable, and that number a that's being squared are the x-intercepts. While over here, since b is the smaller number, and b is underneath the x term, Now I realize that the x-intercepts are at plus or minus b. So this is very helpful because now we can see the x-intercepts without having to go through the work every time. We could simply look at the number attached to x. Y-intercepts are found the same way, except now we're setting x equal to 0, which now gives us y squared over b squared equals 1. And same thing on the other side for the vertical ellipse, we have y squared over a squared equals 1, because the entire term with 0 cancels out. Cross multiplying gives me that y squared equals b squared, or over here, y squared equals a squared. And taking the square root now gives me my y-intercepts. So notice something important here is that in order to look at this equation, this value of a describes the x-intercepts, while this value of b describes the y-intercepts. Likewise, if you look at a vertical ellipse, the process is identical, except now the larger number, a, is going to be what the y-intercepts are, while the b value describes the x-intercepts. So in general, a horizontal ellipse has what we refer to as its major axis on the x-axis. And the reason for that is if the larger number is a, then it's going to spread more in the x direction, and therefore the longer of the two axes is going to be horizontal. While for a vertical ellipse, a is the larger number, so it's going to spread more in the vertical direction, and therefore we say that the major axis is on the y-axis. So let's take a look at an actual example with our values of a and b, and now we would like to graph this equation. Now if we take a look back, remember that the equation for an ellipse is supposed to be x squared over something plus y squared over something equals 1. So what if we see that it's equal to 100? Well, we need to make this equal to 1 by simply dividing every term by 100. And now if I cancel out the common factors of 4 and 25, we get the equation x squared over 25 plus y squared over 4 equals 1. Well, now we should realize that 25 represents 5 squared and 4 represents 2 squared. So we saw on the previous slide that the 5 represents the x-intercepts, while the value of 2 represents the y-intercepts. In other words, it represents how far to spread in the x direction and the y direction. So this is a horizontal ellipse because the x value has a larger value of 5. And so if we take a look at the center being 0, 0, we can now plot in the x direction 5 units away from the center. So we move 5 units to the right and 5 units to the left, which is why these are both our x-intercepts. But now if we want to find our y-intercepts, now we simply move 2 units in the y direction, which is why we're spreading more in one direction than in the other. This is why it's not a circle. If it was a circle, we would be spreading the same amount in all directions, but not in this case here. So when we draw our graph, we could see that horizontally, this axis is larger than this axis right here. This longer axis is referred to as the major axis, while the smaller axis is referred to as our minor axis. More importantly, we can label these points as vertices or co-vertices. Just like with a parabola, the vertex was the lowest point of the graph, or where the graph changed direction. Each of these are considered vertices as well, but we can see that the endpoints of the major axis, the longer axis, are referred to as our vertices, while the endpoints of our minor axis are technically vertices as well, but we refer to them as co-vertices because they're part of the smaller axis. So why don't we take a look at an example now to where the center is not going to be at the origin, but instead it looks more like a circle, to to where we could see that the center will be at HK. The same scenario occurs to where if the A value, which is larger, is attached to X, then it will spread more in the horizontal direction, while if it's vertical, we'll see that the larger value is attached to Y. So if we take a look at this example, we can see that this is very similar to the previous problem because of the denominators. But the only difference now is that the center has now moved. We could see that A is equal to 5, which is attached to X, and B is equal to 2, which is attached to Y. But notice that if the center is not at the origin, we should see now that 2 will cause this quantity to become 0, and -3 will cause this quantity to become 0, which is why the center is at HK, or 2, -3. So when we plot our center here at 2, -3, we now have to start moving away from the center, whatever the amounts for A and B tell us to move. So notice that now the X and Y intercepts are not going to be at 5 and 2, respectively. Now I realize that in order to find the vertices, I have to move 5 units in the X direction away from the center. So when I move 5 units from the center, then that means that I'm going to keep the same Y value of -3, but since the center had an X coordinate of 2, I have to add 5 to get 7 and subtract 5 to get -3. So our vertices are -3, -3, and 7, -3. Now we have to find our co-vertices by spreading 2 units in the Y direction. But remember, that's 2 units from the center. So we need to move 2 units upwards and 2 units downwards, which means that the points will have the same X coordinate as the center, but the Y coordinates are 2 units higher and 2 units lower, which is why these are our co-vertices. Once you have all 4 of those points, you can now construct your graph. So notice that this is the same ellipse as the prior example that we had, but instead of it starting at the origin and spreading to -5 and +5, the center has now changed to +2, -3. So this graph is the same graph, except it's shifted right 2 and down 3. So now I'd like to find a couple of very important points that are part of an ellipse, like we talked about at the beginning. The foci, or the 2 focuses, are actual points in the center somewhere along the major axis that if I connected my string to, that's how I'd be able to draw my ellipse. So the foci are a couple of important features of this graph, but the problem is, how do we find these foci? So taking a look at a standard ellipse here, we should recognize that the center is right in the middle of the vertices, and it's right in the middle of the co-vertices. Notice that each of these vertices are the endpoints of our major axis, while each of these vertices are endpoints of our minor axis, which is why we call them co-vertices. Now what we should recognize at this point is that this is the standard form of our ellipse. A represents where the vertices are, B represents where the co-vertices are. So I just simply spread A units in the X direction and B units in the Y direction. Now I should realize that there are a couple of important points that we refer to as a focus. Plural for focus is foci. So we're trying to find out where those foci are. Now the distance away from the center for the foci is referred to as C. So the question now is, how can we find those C values where the foci are going to occur? So we're going to go through a proof to determine a formula for how to actually find C. So the first thing to recall here is that regardless of what point I choose, let's say I choose this black point on the graph, the distance from the focus to that point, and then that point to the focus, is always going to be the same. So the combined distances from one focus to any point on the ellipse and back to the other focus will always be the same, no matter what point you choose. So why don't we choose the point that's way over here at the right vertex? Let's see what we notice about D1 plus D2. Well, notice that D1 extends from this focus all the way to the vertex. And then when I go back to the other focus, the red length is referred to as D2. So what if we were to move that distance called D2 to the opposite side over here? Notice that what we should see is that this distance is the same as this small distance on the right. So that must mean that the total distance of the purple, D1, plus the red, D2, is actually the entire length of the major axis. So since the left length is A and the right length is A, then that means the D1 plus D2 is 2 times the A value. Turns out that that's true no matter what point you pick. So what if we were to now move that point on the ellipse to be straight up at one of the covertices? Now I should realize that D1 plus D2 has to equal 2A, or 2 times whatever this number is. But notice, considering it equals 2A, and both of these distances are now the same, that means that each of those distances is considered A. So the beautiful thing about this is that if D1 and D2 remain the same length, and the entire distance is 2A, then recognizing that this value is A allows us to form a right triangle. Notice that this orange length we called C. This green length was B, the distance for the covertex. And we now know that this diagonal connecting the vertex, or I'm sorry, connecting the focus up to the covertex is considered A. Now that we have a right triangle, we can use the Pythagorean theorem to find the value of C. Now I see that C squared, this leg, plus B squared, which is this leg, is equal to the hypotenuse squared, which is A squared. And so notice, if we already will know A and B because of the fact that we have our original equation, we can simply solve for C by subtracting B squared. And now to solve for C, take the square root. And I can find my C value for my focus simply by using each of these two denominators. In order to find C for the focus, we simply take the square root of A squared minus B squared. So this formula is now going to be used for the same example that we just took a look at. But before we do so, let's go ahead and now take a look at the last type of feature of an ellipse. We should notice that some ellipses are going to be more elongated in one direction than the other direction. So let's take a look at this ellipse on the right. We can see that this seems to be more elongated vertically than it is horizontally. But then we look over here and we should see that this one is not as elongated as the ellipse on the right. We refer to this as the eccentricity of the ellipse. Eccentricity is given the variable E. So notice that the eccentricity is always going to be a number between 0 and 1 that describes how close the focus is to the center in comparison to how close the vertex is. So if we take a look at this first one, we should realize that C is the distance from the center to the focus, while A represents the distance from the center to the outer edge or to the vertex. The eccentricity can be found by comparing how big C is to A. So we should realize that this one here has a smaller eccentricity because C is actually further from A, as opposed to the one on the right, where we recognize that C is pretty close to A. So because the focus is so much closer to the value of A, that means that this is going to be a larger eccentricity. So therefore, in order to find the eccentricity, we're simply taking the ratio between C and A. In other words, the eccentricity, called E, is nothing more than the fraction of C over A, which is why you should recognize that this number is between 0 and 1, because C, being the focus, is always inside of the vertex. So C is always less than A, and therefore the eccentricity for an ellipse will always be between 0 and 1. So let's take a look at an example, rather the exact same example that we did on the previous slide, to where we recognize that this has a right shift of 2, and it shifts down 3, so that's why the center was at 2, -3. We also recognize that I had to spread 5 units in the x direction and 2 units in the y direction, which is how I ended up getting my graph. But now we can find the foci. These yellow foci can be found by simply using the formula C equals the square root of a squared minus b squared, as we derived earlier. We already know what a squared and b squared are. A squared is 5 squared. B squared is 2 squared. They're given from the original equation. So all I'm doing is saying that C is the square root of 25 minus 4, which means the C value is the square root of 21. So notice the distance from the center to each focus is the square root of 21. Now that's the exact value, but if we wanted to actually plot this, we'd have to come up with a decimal value on our calculator. We find out that C is 4.58. So what I'm really doing to plot the foci is I'm starting at the center, and instead of going out 5 units, which takes me to the vertex, I'm going to go out 4.58 units and plot my foci. So I simply have to add the square root of 21 onto the x coordinates. So when I add and subtract square root of 21 from the x's, I simply get 2 minus that square root and 2 plus that square root. The last thing we want to find is our eccentricity. It appears that this one is pretty eccentric. It's pretty elongated. It's spread out quite a bit in one direction. And the reason we're going to be able to see that this has a pretty large eccentricity is that the value of C, root 21, is pretty close to the A value of 5. So remember that E is nothing more than just the square root of 21 over 5, because of the fact that this was our formula. And now, if I were to change this into a decimal, I'd see that the answer is 0.917. Notice that that's a value that's less than 1. But what that indicates is that the focus distance is about 91.7% the total distance to the vertex. So the closer the focus is to the vertex, the larger E will be. The smaller this value of E is, the closer the ellipse will be to a circle. So if we find the foci are really close to the center, then we're going to notice that the ellipse is much more circular.